So up to now, we've been focused on reviewing what we have already learned in Calc 3 for vectors that are two-dimensional or three-dimensional. In other words, vectors that have two entries and vectors that have three entries. But in linear algebra and in lots of mathematical applications and computer science applications, it's common to deal with vectors that have more than three entries, that are four-dimensional or five-dimensional or 10-dimensional. So today we're going to start to talk about higher dimensional vectors like that. So to make sense of 4, 5, 6-dimensional vectors, we need to change the way we understand vectors. In physics, we might treat a vector as a quantity with magnitude and direction. That's the physics definition of a vector. But in mathematics and in computer science, we don't tend to think about vectors this way. Instead, we usually think about vectors as just a data structure containing an ordered list of numbers. And if a vector is just an ordered list, then it totally makes sense that you might have 4 entries in your list, 5 entries in your list, 6 entries in your list, etc. Now, when you understand vectors just as an ordered list of numbers, you begin to see physical quantities that can be expressed in vector format. For example, colors. Colors can be thought of, especially in a computer context, as a three-dimensional vector. A vector containing as its first entry the color's red value, in its second entry the color's green value, and its third entry the color's blue value. So often in computer work, we represent colors as three-dimensional vectors, this ordered list of values, red, green, and blue. If you're dealing with an image that has transparency, like a PNG image, a color might also be represented using a four-dimensional vector, an ordered list of numbers where you have the red value first, the green value second, and the blue value third. But then you also have a fourth value called alpha. And the alpha value tells you how transparent or opaque your color is. So here's our first four-dimensional vector, just a color with a sense of how transparent that color is. Here's another example. Suppose I'm teaching a class and the class has 35 students in it, and all of the students takes a test. Then the exam scores for these 35 students can be stored in a vector that has 35 entries, a 35-dimensional vector. So exam score of student 1, exam score of student 2, exam score of student 3, and so on and so forth until you get to exam score of student 35. And this would be the 35-dimensional vector used to store the data about the exam scores that these students got. Now, we will be using the following notation very often in this class. Notation for the set of all vectors that contain n entries, the set of all n-dimensional vectors. So the notation is the letter R with an extra leg in the back. R and then an exponent of n. This refers to any and every vector that has n entries in it. So for example, if you see the notation R3, this is referring to all of the vectors that have 3 entries, A and B and C, where A can be any real number, B can be any real number, and C can be any real number. So R3 is the set of all possible vectors with 3 entries.
Editing Sam here. Almost forgot to mention, here is the notation for and definition of the standard basis vectors for R4, the four-dimensional equivalent of the vectors I hat, j hat, and k hat. Standard basis vectors for Rn are defined similarly.
Now let's talk about operations and arithmetic on vectors that have more than 3 entries. Fortunately for us, the formulas that we've learned to do calculations on vectors in 2 dimensions and 3 dimensions extend into higher dimensions in exactly the expected way. So for example, if I have, and let's practice using column notation now. If I have a vector that has 4 entries, let's say 5, 6, minus 1, 2, and I add that to this vector, again in column notation, that has entries 3, minus 4, 0, and 1. If I want to add these 4-dimensional vectors together, then I can just do that component-wise. I can add together these top entries, 5 plus 3, and that will give me a top entry in the result of 8. The second entries, 6 plus minus 4, I can add together, and that gives me a result of 2. The third entries, minus 1 and 0, give me a result of negative 1. 2 and 1 gives me a result of 3. So vector addition, once again, is just component-wise. Vector scaling is also just component-wise. So if I have 5 times the column vector, let's say 1, 2, 3, negative 4, and negative 2, if I want to scale this 5-dimensional vector, all I have to do is scale each of the 5 entries one by one. So 5 times 1, 5 times 2, 5 times 3, 5 times negative 4, and 5 times negative 2. Exactly the same method works. If I want to find the length of a vector that has several entries, I can use exactly the same kind of formula that we had in 2 and 3-dimensional space. So if I define a vector v to be the column vector 1, minus 2, 2, minus 3, and I want to find the length of that vector, I can just square root 1 squared plus negative 1 squared plus 2 squared plus negative 3 squared. Square all of the entries, add all of the results together, and then get the square root of the result. So this is 1 plus 1 plus 4 plus 9. So that's what, 15? So square root of 15 would be the length of this 4-dimensional vector. And likewise, dot product and projection and everything else, that works exactly the same in higher dimensions as it works in 2 and 3 dimensions. So let's define, for example, a column vector v who has 3, 2, 4, 1 in its entries, w which has negative 1, 0, 1, 2 in its entries. If I want to find the dot product between these vectors, v dot w, all I have to do is multiply together the first entries, multiply together the second entries, multiply the third entries, multiply the fourth entries, and then add all of the results together. So again, it's exactly what it should be based on what happened in 2 dimensions and based on what happened in 3 dimensions. The only vector operation that really doesn't extend into any other dimension except for R3 is the cross product. Cross product specifically is only for 3D vectors. It's not viable, and there's no formula for cross product in two-dimensional space or in 4 dimensions or 5 dimensions or 6 dimensions, etc. Now, side quest, let's talk a little bit about vectors as a coding data structure in programming. And let's talk about one of the major advantages of vectors and the reason why we use them so much in a class like linear algebra. Imagine that I have the test scores of 35 students, and I want to take all of those test scores and convert them to percent scores so I can put them into the grade book. Now, when you're just getting started as a programmer, what you usually end up doing in a situation like that is setting up a loop, setting up what's called a for loop, for example. And this basically is saying I'm going to get all of my test scores, and then one by one, I'm going to take each score, I'm going to divide it by the exam's maximum number of points, and I'm going to multiply that by 100, and that's going to turn that individual score into a percent. And so this is calculating these scores one by one, doing a single separate calculation for every single student and every single student's test score. But as a programmer, if you use vectors to do this conversion, you can get the calculation done a lot faster. So you can set up something like this. Instead of storing the scores in an array, store them in a vector, and then use vector scaling to do the conversion. You have a vector here that contains all the students' scores, divided entirely by the maximum number of points and multiplied by 100. And the advantage, especially in coding, of doing this conversion as a vector instead of as a for loop, if you do vector calculations in a computer, the computer is like, okay, my CPU has multiple cores, and each CPU core is basically an employee who is running calculations in your computer. If you vectorize your calculations, if you do them in vector format as opposed to a for loop, the CPU will automatically distribute the calculation amongst all of the cores in your system, whereas a for loop will just queue up all the calculations and give them to a single CPU core to do instead. So if you're on a computer like mine, where my work computer evidently has 14 cores, vectorizing your calculation allows you to split those calculations and distribute them among the 14 cores instead of loading all of your calculation onto a single core and losing a lot of efficiency by doing that. You see a lot of indie games and new game developers making this mistake of not utilizing all of the computer cores and only using one computer core or maybe two. And that's why video games like RimWorld or Oxygen Not Included tend to run pretty slowly as the game goes along, despite having basic graphics system. So be mindful, especially if you have any coding interest, of using vectorized calculations as much as possible. Another side quest, let's talk a little bit about how higher dimensional vector dot products are used in recommendation algorithms. So if you're on, for example, Netflix, Netflix has in its back end a very, very large matrix that it's using to store the ratings that all their users have given all of their movies and films. So for example, for me, I loved the movie Frankenstein, so I gave Frankenstein a really high rating. Netflix has stored my rating of the movie Frankenstein in a matrix somewhere on their servers. Now, the different columns of this matrix correspond to Netflix's different users. So, for example, Sam Smith, have a certain column in their data storage. And each row of the matrix corresponds to a different show or film. So the movie Frankenstein has some row in the matrix that is storing all the different user ratings that it has received. Now, I cannot possibly, like, Netflix's actual matrix is going to be unimaginably large, right? Like hundreds of millions of columns and hundreds of thousands of rows corresponding to all of Netflix's different users and all of their different shows and movies. So let's hypersimplify this situation and consider a matrix where we only have 3 users and they have ratings for 4 movies. So here's user number 1. They did not like the first film at all, so they gave it a rating that I'm storing as 0 in this matrix. They liked the second movie okay, so I stored it as a 1 to say that they liked this. And they loved films 3 and 4 a lot. So I have a 2 here stored in the matrix to represent that they loved films 3 and films 4. Now, the second user loved the first film, loved the second film, but did not enjoy film 3 or 4. So we have a 2 and 2, a 0 and a 0 in their column. And then finally we have user number 3. Now, user number 3 loved the first movie. They liked the second movie. They liked the third movie. But they have not seen the fourth movie yet. So the question is, should Netflix recommend film 4 to the third user or not? Do we think that user 3 will like film 4, or do we predict that user 3 will dislike film 4 is the question. So to make that decision, we're going to use cosine similarity, which we introduced briefly in the previous lesson. Cosine similarity is used to determine the similarity between user number 3 here and the other 2 users in the matrix, user 1 and user 2. So we use the cosine similarity formula to measure the similarity between user number 3 and user number 1. Based on the films that both of them watched, how similar are their viewing tastes? So we're going to take the dot product of these 2 vectors. That's what you're seeing here. We're going to take the length of the vector representing user 3, their column. So that's what you're seeing here in terms of the square root 6. And then we're going to take the length of user 1's column, focusing on the 3 films that user 1 has seen that user 3 has also seen. And so based on that calculation, the similarity between user 1 and 3 is giving us a value of 0.55. That's the cosine similarity between these 2 users based on the films that both of them have watched. We can do a similar calculation to measure the similarity between user 3 and user 2. We find that the cosine similarity between user 3 and user 2 is 0.87 units. So because the cosine similarity here is larger than the cosine similarity here, we can conclude that user 3 is pretty similar in their viewing tastes to user 2. User 3 is more similar to user 2 than they are to user 1. So what we're going to do is we're going to consider what rating did user 2 give to the last film, and based on that, we're going to decide whether the last film should be recommended to the third user. The user 2 did not enjoy the last film. User 2 gave the last film a rating of 0, not for me. So because user 2 did not enjoy the last film, and because user 2 and user 3 have a large cosine similarity, Netflix is going to decide, no, we will not recommend film 4 to the third user. We will see if there is something else that we could recommend instead. So this kind of algorithm where Netflix is giving recommendations based on the ratings of similar users, something like that is called a collaborative filtering algorithm. To summarize, in this episode, we introduced higher dimensional vectors. To make sense of higher dimensional vectors, we think of vectors just as a data structure containing an ordered list of numbers, beginning to move away from the kind of vectors that we worked with in physics. The advantage of representing an ordered list of numbers in a vectored format is, first of all, it allows you to use all the same formulas that were introduced for two-dimensional and three-dimensional vectors, like addition, scaling, dot product, length calculation, projection, etc. The second major advantage of storing data in a vector as opposed to some other data structure is that it unlocks vectorized calculations, which are automatically distributed among all your CPU's cores, which makes the calculations on your computer run much faster. And one example of a vector calculation as used in a real-world context is for things like recommendation algorithms, where vector length and vector dot product are used to calculate cosine similarity, which is used, for example, to determine how closely one user's tastes resemble another user's tastes, so that what user 1 likes can be applied to user 3, what user 2 likes can be applied to user 3, depending on how similar they are.